This is a model of x equals y squared with the equilateral triangles with the cross section about 1/8 of an inch thick.
Okay.
64 of them.
And how did the volumes compare?
They were different.
This is apparently rather a common thing.
Yes. Quite different.
What were they in fact?
I might have messed up here, and I mean, I probably did. For the model, or for the the model is it was 56.29 cubic inches. I think that's wrong. I don't know anything about anything. For the
well, it is a cubic inches. Is that the unit?
Yeah, it's a volume.
Okay, sure. Yeah.
And it's and then for the what it would really be if there were infinite amount of triangles would be around I think I got 55.42 inches, 43 cubic inches.
It doesn't sound all that different.
Right? I mean,
yeah, it.
Yes.
Yeah. Okay, well, I can shift it over here to Mitch fairly easily. Yeah,
I did a graph of the sine curve with cross sections of squares. There's 79 of them. I think.
Not an even number of squares?
No, like the way when I first started like it started around the negative pi to 0, and then when I worked over to this one, it was like not even.
Well, no, you just explained how it happened. You had trouble squeezing the last one in, and yeah.
And then
no problem.
About an 80% error.
Yeah.
Like on the calculator, if like if there are infinite number of squares, I guess. Should have been about 122.2310 cubic inches. I got 220.2428.
Yeah, reasonably substantial.
Riddle me that.
Yeah. So there's something going on. You're all going to hand in your the sheet that explains all this.
This is a cosine of x, y equals cosine of x graph, where the cross sections are regular hexagons, and each side is the length of y equals cosine of x. For the area of the model, I got 4.081 units, so like 1 unit is from here to 1.
Okay, good.
And that comes out to 326.4839 millimeters cubed.
Okay.
Because my scale is 5 millimeters is 5/80 units is 5 millimeters.
Okay.
And for the actual area, got the same number.
You got the same number. Could you?
The error was like 0.001.
Awesome. Yeah, but you should be saying volume every time.
Volume.
Yeah. Okay. So, well, let's see, I can bring it over here to Timmy, and.
So this is a circle with radius 3, so x squared plus y squared is equal to 9.
Okay, hold it still, and let me zoom in on it. Okay, good.
Or y is equal to plus or minus square root of 9 minus x squared.
Okay.
And then it has cross sections of right isosceles triangles where the base and the height are the same, and that the base is the diameter of the circle. Then there are 30 cross sections, and with that, volume is approximately 71.92 cubic inches, and then with the integral, it's approximately 72 inches cubed.
Okay, so you got yours to come out pretty well. What do you got?
So I have a cross section of 345 right triangles along the parabola y equals x squared. I got my my volume was approximately 13.5 cubic inches, and my actual volume was 8.77 cubic inches. So it was
I did the sine curve with a cross section of circles, and my volumes were not too far off. But
circles or semicircles?
Oh, well, semicircles.
Okay, yeah. There's a difference. You could have done circles.
Right.
Yale has something that goes all the way through. It's,
and
but
then my area was 125.6 cubic centimeters, and
what was your volume?
Oh, sorry, volume. That's what I meant. And then when I calculated, and then the actual one was 158.98 cubic.
Okay. So who's next?
Okay, I did a circle with a radius 3. So the equation is x squared plus y squared equals 9, with cross sections of equilateral triangles in an xy plane. And the volume I got from the Riemann sum was 61.4072 cubic inches, and the approximated volume from the integral was 62.3538 cubic inches.
So not too bad.
No.
Yep. Yeah. I wonder what the problem is with these guys who are not. I'm gonna have to see if I can figure out. I get it trained on this. Okay, tilt it toward the camera. So.
Okay, so
the other side's got writing on it, doesn't it?
Well,
Yeah, so much. Yeah, sure. It's good, but talk about it with the writing visible there.
Okay, so
now point it toward the camera. The camera's been running this whole time.
okay, this is a three-dimensional graph, and this area right here is between two parabolas with the equation 0.5x squared minus 2 and 2 minus 0.5x squared. It has cross sections of circles, and the scale is 1 inch to 1 inch or 1 inch to 1 unit for simplicity.
God, that seems to be a wise choice, actually.
Yeah. Doing the integral, I got the area or the volume to be 26.8083 inches cubed approximately, and I got the same thing with just Riemann sums.
Just adding up the volumes.
Yeah, but it's not really circular because this area, I didn't include that because I didn't want to have to cut out like, I don't know, 1/8 of an inch, and then that would shrink the Y.
Yeah, no, that you're what you're doing obviously is taking the theoretical circle and multiplying it by the thickness. So it's
this just is a little longer than
yeah. So is that are those semicircles glued onto each side, or are they?
I actually made circles with a compass and I cut them in half.
But
exact.
Okay, so you didn't cut a hole in the foam and put the circles in.
Cut them in half.
Yeah. Sounds like you made some extremely practical decisions. And, very good. Okay, now let's. Now, did you do the same kind of thing that he did, glue them on both sides, or did you cut a hole in the foam?
No, I cut them in half.
Okay, yeah.
So
good for you.
I ended up doing the intersection of y equals x over 2 and negative x over 2 with the cross sections and diagonal of the square. And I had 1 unit equaling 9 centimeters. It's a little difficult, but that's alright.
Yeah.
And my integral volume was 7,776 centimeters cubic centimeters, and the actual volume I came up with 7,938 cubic centimeters.
Yeah,
so it's not that far off.
Okay, yeah, that's about as far off as you'd kind of expect.
Yeah.
Good sized model like that. Yeah, no,
that's square.
Yeah, no, that is. Well, good job, everybody.